Okay, KSP, the solubility product. When excess solute is in equilibrium with its aqueous solution, a special case of dynamic equilibrium is established. The equilibrium constant gets a new symbol, KSP, and a new name. It's called the solubility product constant. The solubility product constant is the value obtained from the equilibrium law applied to a saturated solution. It is the product of the molar concentrations, product is multiply, the multiply of the molar concentration of ions in saturated solutions. So the KSP value, just like the other K values, indicates how far to the right the products we make, and in this case the products are ions. So it will indicate how soluble a compound is in water. So if you have a low KSP, you have low solubility. We need to find this information in industry to precipitate out chemicals, in medicine to help make x-rays. It's how fudge and stalagmites are formed. It's also how kidney stones form and why people get gout. So molar solubility is the amount of moles of a solute that can be dissolved in a given volume at a given temperature. In the ice tables, molar solubility is the value for X. Ionic solutions and concentration calculations need to be reviewed for this. So let's write the equation for the dissolving of lead to iodide. So lead to iodide, write it as a solid. We don't have to write in the water because it doesn't react with it. And we form lead 2+ ions and iodide ions. Now it's really important that you remember to write the proper form for your ion. It's not I2. And to balance it, we need a coefficient of 2. So write the equation for the reaction of silver nitrate and sodium chloride. So silver nitrate is AQ because all nitrates are soluble. Sodium chloride is AQ because all group 1 metal chlorides are soluble. Now this part has a single arrow. This is just a typical double displacement reaction. So we form silver chloride and sodium nitrate. Now, all nitrates are soluble, so that's an AQ. But silver has low solubility with chloride, so that is a solid. So we're using our solubility tables for this. Now, from this, you would get your solubility equilibrium. Silver chloride is our solid, so it would be an S, and then it will come to equilibrium with its ions. Again, remember, chloride is Cl1-. So then, the K value for these will be called a KSP, and it's products over reactants. So the products are the AQ ions and the reactants are the solids, but don't forget, solids don't change enough to be considered unchanged. So therefore they become part of your K value. So what you end up with is your ions. So KSP is going to be equal to the silver ion concentration times the chloride ion concentration. And for the first one, the lead iodide, KSP is going to be equal to the lead 2+ times the iodide to the second order. Because these should be over the solid, but the solid becomes part of the K because it's also constant. Okay, a little bit of review here. If you have 250 milliliters of a 0.2 molar, and that is 0.2 mole per liter solution, you dilute it to 1 liter. What is the new concentration? So don't forget to change your milliliters to liters because we have to have liters for our concentration. And this is a case where you haven't changed the number of moles of silver nitrate. You've changed the moles of water present. So we can use the dilution formula from grade 11. And we will be solving for the second concentration, the dilution. So C1 V1 over V2 is equal to C2. So 0.250 liters times 0.2 moles per liter divided by 1.0 liters. So this is equal to 0.050 moles per liter. So whenever you do a dilution, your second concentration will always be less than the concentration of your initial concentration because you're diluting it. There's going to be more water, less, well, the same solute, but more water. So becomes more dilute. So basically what you end up doing is, if these are particles of my concentrated solution, my 0.2 molar this is now okay, so that should be the same number of particles. So this is basically my dilute. There's a lot more water, but the same number of solute particles. So there's a lot more space between the solute. Okay, you will either be asked to calculate the molar solubility or the KSP value, typically in a question. So what is the molar solubility? X of lead iodide in water. So lead iodide solid, lead 2 plus and 2I minus. So what do we have to do here to set this up? What do we need? That's right, we need an ice table. So basically what we do is set up an ice table. We don't need to worry about the solid because it's not part of our K expression. But initially, we have 0 products. Then they go through the change, so plus x and plus 2x. So that equilibrium, 0 plus x is x, 0 plus 2x is 2x. So our KSP is going to be equal to PB2 plus I minus squared, because it's second order, so x times 2x squared. Don't forget that squared. And this is equal to 8.5 times 10 to the negative 9. So this side is equal to 4x squared times x, so 4x cubed. So divide both sides by 4, and then take the cubed root of each side to solve for x. So our X is going to be equal to 1.3 times 10 to the negative 3, and it's moles per liter because it's a concentration. So the molar solubility of lead iodide is 1.3 times 10 to the negative 3 moles per liter in water. Because your KSP is so small, times 10 to the minus 9 tells us that very little solid actually dissolves to form products, our ions. So it makes sense that our molar solubility, the amount that's present at equilibrium, is actually fairly small. 1.3 times 10 to the negative 3 moles per liter. That's very low solubility. Okay, the concentration of silver ions is 2.567 times 10 to the negative 4 moles per liter in a beaker containing a saturated silver carbonate solution. What is the KSP? So you're either going to be asked to find the molar solubility, the X value, or you're going to be asked to find the KSP value. So we know that we have the concentration of silver. So we have to set up a balanced chemical equation. So silver carbonate, solid, dissolves into 2 silver ions and the carbonate ion. Now, the molar concentration is fairly small, times 10 to the negative 4, so it stands to reason that our KSP is going to be fairly small as well. Very little of the solid dissolves in water. So what do we have to do now? What do we have to set up? That's right. We need an ice table. Okay. So initially, change and equilibrium. So solid, solid, solid. 0, 0, plus 2x, x, 0 plus 2x, 0 plus x. So this is our line that goes into our K expression table. Now, we also know that the equilibrium concentration of silver ions is this. So we can solve for x. So it's 1.2835 times 10 to the negative 4 moles per liter. So our KSP expression, concentration of silver ions, second order, carbonate, first order. So 2.567 times 10 to the negative 4 squared, and 1.2835 times 10 to the negative 4. So this is equal to 8.46 times 10 to the negative 12. So we really do have a very small KSP. So very little silver carbonate actually dissolves into its ions. So it's very low solubility. All right. What is the molar solubility of lead iodide in a 0.1 molar solution of sodium iodide? Okay, sodium iodide is very soluble. We would get sodium ions and iodide ions. So the difference here from our first example is that we will have a starting concentration for just iodide, because lead iodide and sodium iodide have a common ion, and that is iodide. So we still write the solubility equation for just lead iodide because that is the one that's present as a solid. And now what we're going to do is we're going to figure out, we need an ice table. We're going to figure out what the difference is between the solubility with a common ion or pure water. So we're going to compare those two. So there's no lead added, so initially it's 0, but we have 0.1 mole per liter of iodide. We do not multiply this by 2 because we use the coefficient from the sodium iodide. So 0.1 mole per liter sodium iodide times 1 iodide per sodium iodide. So you have to use the coefficient from your other solution, where you got the common ion from. Okay, so the change is plus x plus 2x. So now at equilibrium, we have x and we have 0.1 plus 2x. So set up your KSP. It's going to be equal to lead 2 plus. Always do this part. It's proper form. Write out your K expression without your values. So then this is x, and this is 0.10 plus 2x, and this will be squared. So this is equal to the same KSP as we used before. So now if you look at this, we've got a term in brackets that we should probably use FOIL from, which means we'd have to use the quadratic equation. However, don't forget, you're a chemist. We are efficient. So we can say, okay, what happens if 0.1, the initial concentration, over our K value is greater than 1,000? Then we can make our assumption that 0.1 plus 2x is approximately the same thing as 0.1. So if this is much greater than 1,000, we can make that assumption. And guess what? It is. So therefore, 0.1 plus 2x is 0.1. All right. So now we have 8.5 times 10 to the negative 9 x times 0.1 squared. So now x is going to be equal to 8.5 times 10 to the negative 9 divided by 0.1 squared. So x is going to be equal to 8.5 times 10 to the negative 7 moles per liter. Okay, just move this up a little bit so that we can see things better. So our molar solubility decreased from when it was in pure water. When it was in pure water, the molar solubility was 1.3 times 10 to the negative 3. So this was pure water, and this is with a common ion present. So it went down quite a lot, so less soluble. Now this makes sense though, if you think about it. Think of Le Chatelier's principle. your system will shift to oppose a change on the system. So if we increase this value here, the system will shift to use it up. So it will shift to the left. So it will make more solid, and the value for these will decrease. So we're applying Le Chatelier's principle here. And this effect is called the common ion effect, and it's based on Le Chatelier's principle, because we're increasing a concentration of a product. The system shifts to use it up, so it will shift to the left, and the left, of course, means more solid, less dissolving. In some cases, it will be required to determine whether precipitation will occur in a given concentration of ions. So this is our quotient rule again, and we compare our Q value to the KSP to make a decision on whether or not we will see a precipitate. Predicting precipitation using Q. If Q is greater than KSP, we'll get a precipitate because we have a supersaturated solution. But if Q is equal to KSP or Q is less than KSP, we will get no precipitate. So we're going to do an example where we have calcium chloride solution added to sodium sulfate solution, and we need to determine will a precipitate form. So you have to write out your reaction, your double displacement reaction, and then identify the species that would precipitate. And then you write out the chemical equation for it dissolving in water, like we've been doing, to form its aqueous ions. You figure out what the concentration of each ions are now, using the dilution. Because we've mixed two volumes, we have a new total volume. So it's like we've done a dilution. We calculate our Q, and then we compare our Q to the KSP. So let's do this problem together. So we have calcium chloride, and we have sodium sulfate. So we would form, through double displacement, calcium sulfate and sodium chloride. Now, all chlorides are soluble if they are with ammonium or group 1 metals, and calcium sulfate is our solid. So then we would have calcium sulfate solid dissolving into its ions at equilibrium. So now what we have to do is figure out the concentrations of our species or our entities. So we have 50 milliliters of calcium chloride. So 50 milliliters, convert that to liters, and we've got 0.05 liters. And our concentration is 0.001 mole per liter. We also have 50 milliliters of sodium sulfate, and this concentration is 0.01 mole per liter. So what we have to do is figure out the new concentrations after we've mixed these two solutions together. We had 50 milliliters of each, so when we add them together, our new volume is 100 milliliters. So we have to apply the dilution equation to both of these solutions to figure out what the new concentration of the ions for sulfate and calcium are, based on the fact that we've diluted to 100 milliliters. So C2 is equal to C1 V1 divided by V2 for both of them. So for calcium, it is going to be 0.001 times 0.05 divided by 0.1. And this would give us the concentration of calcium chloride. So this is 0.0005 moles per liter calcium chloride, but there's 1 calcium for every 1 calcium chloride. So now we know the concentration of calcium ions. Do the same thing for sulfate. We have 0.01 times 0.05 divided by the new total volume. So this is equal to 0.05 moles per liter. Again, this is for sodium sulfate. But because there's 1 sulfate for every 1 sodium sulfate, we can figure out the concentration of sulfate. Okay. So now we know that we have 0.0005 mole per liter calcium sulfate and 0.005 mole per liter sulfate. So Q is going to be equal to calcium 2 plus times the sulfate. So 0.0005 times 0.005, which is equal to 2.5 times 10 to the negative 6. Now, every textbook, every chemistry textbook will have a table of solubilities. So if we look up sulfates, calcium sulfate, we see that the KSP is 4.93 times 10 to the negative 5. So our Q times 10 to the negative 6 is smaller than our KSP times 10 to the negative 5. Therefore, no precipitate forms, because our Q is less than our KSP. So basically, for solubility, you'll be asked to determine molar solubility, your X, or you'll be asked to find your KSP, or you'll be asked to figure out the change in concentration based on a common ion, or you'll be asked to determine whether or not a precipitate forms. And that's it for equilibrium solubility.